We have our final presentation today by Joe Stilwell, and I really like the first two words of Joe's presentation, practical applications. Okay, and the program says practical implementation, but we'll hear more about what Joe has to say. Thanks.
I know we're at lunchtime, trust me, my stomach, I can smell lunch. I'm not gonna spend too long on a lot of this. Breeze through this is pretty high level. If it takes more than 10 minutes, let me know. So Grist Mill Bridge, you guys have seen it a number of times now. Our first fully composite superstructure we've done. Great experience with that bridge. So MaineDOT loves our composites. We utilize it in many facets, not only in the bridge program, but in other parts of the department as well. Got the arch bridges developed here, made by AIT. We're doing composite piles. That's done at Kenway in Augusta. So another Maine company doing composites for MaineDOT. Bridge scuppers, as we all know, steel scuppers will rust out. So we've gone to pretty much exclusively composite scuppers with stainless steel grates. Almost all of our bridges in the last couple of years. Those are also made at Kenway in Augusta. FRP rebar, we put it in so many bridges, it's not even funny. New product that we did, worked with AIT on this one. These are composite utility trench covers to be used down in the port of Eastport. So it will be wet 99% of the time. So a product that will last them well over 100 years. And one of the first composite bridges we ever did, the first project when I started with the department, the Knickerbocker Hillman composite girders. And so we found steel will rust when the coating goes away. So this is kind of a project we did where we used FRP wrap to wrap in place fusion bonded epoxy pipe tiles, because this bridge, epoxy was gone. It was built in 1996. Great superstructure. It was rotten from down below. And one of the things that Roberto showed, 3D printed large additive form used for ballast retainers for a multimodal railroad job up in the county. Supposed to be done at UMaine, had some printer issues, but these were cast at American Concrete and VZ. If you didn't know they were made with composite forms, you were sworn they were made with traditional steel forms. They were that good. And Grist Mill Bridge. Don't need to speak anymore about that one. And this is from the as fabricated at the shop, one of the girder sections for a twin bridge that was installed yesterday. So you've been hearing about how it's resilient and durable. I'm a practical kind of engineer, so I convinced AIT to let me test the material properties of this back when we were doing Grist Mill Bridge. Yes, they gave me a big sledgehammer to smack these things. You can see flexure, the flexure, the rebound. There we go. Sorry. And yes, hit the bottom flange as hard as I could twice. Gotta love slow-mo. So you've been hearing about all these. It's durable, it's lightweight, non-corrosive. Things that people didn't really get into. It's highly repairable. It's really no different than trying to repair your old hotel canoe when you crash into a rock. It's a designer material. There are so many different types of fibers, resins, and cores that you can tailor exactly what your design needs for with the appropriate materials for your thing to minimize waste and put strength where it's needed. And like other people said, not a new material. They've been using this in infrastructure for 25 years. Marine's been using it since the 40s. Aviation's been using it since the 50s. It's not new. It's a new application of a mature material. So these are some of the after pictures of my testing. So as you can see, minor scratching. There was no delamination. It was just minor scuffing on the surface. Zero damage. So that kind of shows the old Tupperware bridges, as people used to say. What are people going to do when they decide to have fun and damage them? Really hard to hurt them when they're designed and built correctly. And zoom in. Yeah, that little spot around that circle. Yeah, that's where I hit it. So from a DOT in perspective, these are kind of the barriers to FRP implementation. Training. John hit this on his. Training is a huge thing. Understanding that there will be nonconformances and need to have established repair procedures. It's inevitable. I oversee the fabrication of every structural component that MaineDOT does. So concrete and steel. I have yet to have a project where we haven't had to have some form of repair during construction. It's one of those inevitable things. Audit programs. This is to give the states and owners kind of assurances that the material they're buying is what it says it is. They're not some guy in his garage throwing a product together. It's actual high quality product that you can bet your life and the traveling public's life on. And of course, specifications, the lifeblood of everything that's built. So in order to handle some of these training issues, there's a lovely thing in the 23 CRF for acceptance. You have to have a third-party certified inspector. And when we were doing the gristmill job with these structural FRPs, that didn't exist. So working with University of Maine and borrowing part of the ACMA's very robust training program, we took the ACMA vacuum infusion composite technician course. So that's the book work and the theory, and combined it with a hands-on practical lab here at the UMaine TID Center at the Kenway Composites Lab, where we did practical layup. We damaged some panels. We went looking for issues. So we got the hands-on experience on how to handle, how to inspect, and how these products are actually built beyond just the theoretical coursework. And at that course, it was myself, my QA inspector staff. We had fabricator QC, because nothing makes more hate and discontent when both the fabricator, quality control, and quality acceptance on the state side have different training. So having everyone knowing the same basic stuff eliminated a lot of any potential issues. And on the other end, we also brought the bridge maintenance personnel in with us, because they're the ones who are responsible for inspecting it ongoing future. So you can't bring in a new product if the people that are inspecting it in the future have no idea what they're looking at. So as part of the non-conformances stuff, working with the fabricator, a definitive process was defined in their quality control plan. And since there are really no standard repair procedures for FRP right now, they have them for steel in the non-conformances guide. They have them in precast from PCI's non-conformances guide. So the other major components of infrastructure, they have non-conformance guides. So working with the fabricator, we kind of came up with standard repair procedures that we could trust for standard issues that would happen, like improper wet out, dry spots. Repaired, looks like it was never there. We had contamination of a resin issue, full depth. Developed a repair procedure. You see the repair there. Since this is one of the gristmill girders, we had the opportunity to instrument this. So we verified that that repair performs exactly like a non-repair section was during live load testing. So air a little bit of dirty laundry here. Show you the extreme of what can be repaired for non-conformances. During one of the UTC test girders, a little bit of vacuum infusion issues with the new form at AIT. As you can see, it's not supposed to look like that. Big old pillow, wrinkly. That is complete non-wet out and non-compaction. That was just one layer, shoved a piece of plastic in there just to kind of see. Rather substantial layup issue. This is not a DOT bought girder. This was one that was going to be set for testing, which makes this perfect. AIT applied the repair procedures that we developed for the girders on a much larger scale. You can see they removed everything all the way down to the center core. That repair girder was then tested at the University of Maine as part of their testing procedure. The repaired girder actually tested better than its sister girder that had no repairs to it whatsoever, as proof that even as bad as it is, you can repair it. So as part of the audit programs that have been recently developed over the last year and a half, as part of one of my AASHTO committees and with input from states and industry, developed an audit program through AASHTO's National Transportation Product Evaluation Program. This is a very robust program which will set a universal benchmark for quality of rebar manufacturers that anyone can, that you will know if you have someone that's been audited through this facility, their quality control plan has been reviewed by the AASHTO committee. And there's an annual audit that is performed by an AASHTO designated inspector. So this is DOT, this is an AASHTO contractor, mostly former DOT personnel, will go to the facility. They will review all the quality control documentation as specified in the quality control plan and in the AASHTO work plan to make sure that the fabricator has actually been taking the quality control samples they're supposed to do. The samples match what they say they're supposed to be, the specifications. And they're following the procedures to give them the best chance of producing a material that is conforming to their specifications. As part of that, a sample will be taken of each bar type, so each bar size, and sent to the AASHTO designated lab for conformance testing for the following properties. The really important ones that in the AASHTO, the design codes say, manufacturers cert on this. So this is a 1 year snapshot in time that the manufacturers that have been audited have produced bar over the course of the year that was randomly sampled that you can verify test reports at a fully independent third-party facility. And then, as John alluded in the beginning, there are specifications out there. This is just a snapshot. I went well higher on the AASHTO stuff because transportation guy knew all those ones. The ACI 440 code has so many specifications and guidelines. It's kind of crazy. This ASC's got their stuff. AMP, which is new NACE and SSPC, is developing a inspector program for bonding, for inspection of FRP bonded to substrates. So the concrete strengthening, steel strengthening. They're developing an inspector course for that. And this is just a sample. If you look at the Canadian, European standards, I could have like 6 slides and not cover everything. So there's no mystique to this. There may not be a 100% defined code for you're looking at, but there is something in one of these codes that you can pull from and apply to what you are doing in order to use quote unquote engineering judgment to create a safe, robust, long-term, durable piece of hardware. And that is the end of my presentation. See, short and sweet, as promised.